After studying this module, you shall be able to know about how nanotechnology is useful in the field of fingerprint science, learn about the semiconductor nanocomposites that are used in the fingerprint detection, and how they are helpful as an aid in latent prints detection. Despite fingerprinting being essentially the foundation technique of modern science, only a fraction of all the finger marks at a crime scene are actually detected. The most problematic of fingerprints are the latent fingerprints or the latent prints that are not readily visible by the naked eyes and that require development by chemical or the physical means. Usually, the choice of the technique for fingerprint development is dependent on the composition of the latent fingerprints, on the type of substrate, and on the ability of the technique to be applied in sequence in the context of the case. Materials such as carbon black and aluminium flake have been used as the latent fingerprint developer for many years, as it was found that they worked well under the particular circumstances, but there are very minimal activity in developing the engineered materials especially designed for fingerprint development. The ideal fingerprint powder will stick to the residues left by the finger, which gives rise to the characteristic patterns that everyone identifies as a fingerprint, but not stick to anything else. Many common materials also stick to the background, making it a clear identification significantly harder to achieve. Nanotechnology is being used to engineer particles so as to overcome this problem. Instruments used in nanotechnology labs or nanoparticles themselves have several uses in forensic science, says Ian Turner, a lecturer in biology and forensic sciences at the University of Durban. Often nanotechnology results in improving the sensitivity of already existing forensic techniques, points out Bruce McCord, professor of forensic chemistry at Florida International University, who worked at the FBI Forensic Sciences Center from 1989 to 1998. The first aspect that is being investigated is the use of nanoscale powders to provide clearer images. Now, we will be studying about the use of photoluminescent semiconductor nanocomposites. Semiconductor materials such as CDS, CDSE, CDTE, INP and INAS, which normally are not luminescent, can become intensely luminescent when particles, typically in crystalline form, become very small, that is of nanometer order in size. Such nanoparticles can be quite robust. They are typically encapsulated with zinc sulfide, silica, or the organic material. This capping is sometimes referred to as the derivatization or functionalization, especially when an organic compound is involved, which is sometimes also referred to as the surfactant. The encapsulation amounts to covering the nanocrystal with a layer of material that may serve a variety of functions. For example, passivation to optimize luminescence efficiency, serving as a site for attachment of conjugating ligands designed for specificity of chemical binding, serving this labeling function itself, serving to solubilize the nanocrystal and preventing aggregation of the nanocrystals. Photoluminescent semiconductor nanoparticles have recently become the subject of intense investigation in the biotechnology arena, mostly for the labeling purposes. The salient virtues that distinguish the nanoparticles are referred also to as the quantum dots, nanocrystals and nanocomposites, depending on the morphology of that particular substrate, from ordinary fluorescent labels are that their absorption and luminescence wavelengths or the colors can be tuned by varying the particle size and that the luminescence lifetimes are long, ranging from roughly 10 to the power minus 8 to 10 to the power minus 6 of seconds, thus making the nanoparticles suitable for time-resolved spectroscopy and time-resolved imaging, with flexibility in terms of useful laser light sources. These features are valuable from a biotechnology perspective and are in principle equally pertinent to the fingerprint context, thus prompting a study of their potential utility in fingerprint detection that commenced in the year 1999. Because of financial and manpower constraints, this investigation has to date only aimed at reduction to practice, that is the demonstration of feasibility rather than workup of routine recipes. Nonetheless, a variety of nanoparticle systems and fingerprint chemistries have been examined for. Now, we will study about the cadmium sulfur nanocrystals in fingerprint detection. Photoluminescent semiconductor nanocrystals may be expected to be used for fingerprint detection in various ways, namely by incorporation into the dusting powder in a manner akin to fluorescent dyes, blending with the magnetic powders by staining, especially once the fingerprint have been exposed to the cyanoacrylate ester or the cyanoacrylate fuming technique, or by chemically bonding to the constituent of the fingerprint residues. In photoluminescence detection of the fingerprint, the staining approach generally tends to be more effective when applicable to the article under examination rather than the dusting procedure. As a preface to the mode of this fingerprint detection technique, the photophysical properties of the cadmium sulfur quantum dots or the nanocomposites are examined for primarily to assess suitability for phase-resolved imaging to suppress the background fluorescence, but also to determine the suitable excitation wavelengths. The employed CDS nanocrystal samples prepared in inverse miscellaneous and capped with diacetyl sulfosuccinate, that is the sodium salt, were obtained from Professor John T. McDevitt of Chemistry Department, University of Texas, Austin. Solubilization of the nanocrystals utilized heptane or a mixture of the hexanes compound. Solutions had quantum dot concentration of milligram per milliliter order. Absorption spectra in these solvents exhibited band edges at about 440 nanometers and very broad absorbance with some structure, but not the absorbance peaks as in a typical atomic or the molecular spectra that increased with the decreasing wavelength to 300 nanometers, means the lower the wavelength in an absorption measurement. They serve to determine the size of the nanocrystals, which were then deduced to have a radii of 3 to 4 nanometers. The nanocrystal luminescence, having a bandwidth of about 100 nanometers, peaked at about 580 nanometers with a second weaker luminescence band in the 400 to 450 nanometer range. In terms of the intensities as a function of the excitation power, the excitation wavelength, solvent system, etc., the luminescence spectroscopy of the nanocrystal tends to be more complex than that of the typical fluorescent molecules, because in nanocrystals one likely has a number of different and quite variable trap states that contribute to the luminescence, including the surface traps as well as the intrinsic semiconductor recombination process. Thus, the spectroscopic features generally need to be examined for the samples at hand in comparison with the literature results, serving as the approximate guide. Lifetime measurements for the heptane solution use the phase shift or demodulation techniques, as has been already told earlier, and employed a helium-cadmium laser operating at a wavelength of 325 nanometers. The lifetime measurement corresponded to the total luminescence that is transmitted to the detector through a long wavelength pass filter. Laser modulation frequencies ranged from 0.1 to 100 MHz. Approximately 70% of the luminescence intensity corresponds to the emission with a lifetime of about 1000 nanoseconds, about 25% to emission with a lifetime of about 70 nanoseconds, and about 5% to emission with a lifetime of 0.54 nanoseconds. This latter is excitonic emission, and the obtained lifetime is in good agreement with the literature that we correlate with. Total luminescence lifetime measurement was made rather than the lifetime measurement at a particular wavelength or a set of particular wavelengths, because fingerprint luminescence imaging usually involves the total luminescence factor. Because staining with fluorescent dyes after cyanoacrylate ester fuming is a very successful fingerprint detection methodology, diacetyl sulfosuccinate capped with the CDS nanocrystals or the cadmium sulfur nanocrystals dissolved in heptane or hexane can be employed in this particular manner. In an experiment carried out, on sample fingerprints were placed on a soft drink can and on an aluminium foil which were fumed with cyanoacrylate ester. The samples were then immersed in the nanocrystal solution for times ranging from a few seconds to a few minutes. The immersion times were not critical. The samples were then left to dry. Luminescence examination under the argon laser operating in the near UV, that is a good excitation regime, revealed amply intense luminescence. Because there was a generally heavy coverage of the immersed sample portion masking the fingerprint in detail, the samples were subjected to gentle rinsing with hexane so as to remove excess nanocrystal deposition, leaving behind the fingerprint detail clarity. Any preferential adherence of the organically capped CDS nanocrystals to unfumed fingerprints would involve the non-polar fingerprint constituents such as the lipids, and these readily dissolve in hexane or heptane, that is particularly the former, which is more aggressive than the latter because of lower viscosity. Thus, the unfumed fingerprints on metal, plastic, glass, etc. could not be developed by the staining procedure that I have already told. However, on black electrical tape, that is the sticky side of that adhesive tape, the unfumed fingerprints could be stained successfully with heptane nanocrystal solution and with heptane rinsing. Now we will be studying about the application of CDS or the Dendrimer nanocomposite. Dendrimers are polymers of tree-like structure that have lately begun to command intense attention in many areas of science, especially in connection with their incorporation with the nanoparticles of various kinds for the purpose of applications that include cancer drug delivery, catalysis, waste cleanup, optical devices, etc. Of the particular interest here is the photoluminescent nanocomposite of the CDS with the starburst or the PAM dendrimer that was first outside the forensic science arena described by Suklal, Hannes, Ploshin and Murphy. The nanocomposite contains nanoparticle size clusters of CDS that are incorporated into the aggregates of the dendrimer molecules. The starburst, that is registered dendrimers, are of particular interest for any practical utilization in the fingerprint laboratories, and the starburst dendrimers are of particular interest from our perspective because they are commercially available, that is of the ordinary, and a must for any practical utilization in fingerprint laboratories. These dendrimers come with either amino or carboxylic terminal functional groups and which are useful for chemical fingerprint processing. The initial CDS or dendrimer nanocomposite study involves the generation of 0, 1 and 4 dendrimer, and the dendrimers come in methanol solution. The preparation in methanol of the CDMS or the dendrimer nanocomposite simply involves diluting the dendrimer solution and adding it to small quantities or aliquots of equimolar methanol solution in equal volumes of the cadmium nitrate and of sodium sulfide. In the absence of dendrimer, the reaction of the cadmium nitrate and sodium sulfide would produce the cadmium sulfide as a precipitate in large clumps. In the presence of the dendrimer, however, an aggregate of the CDS of nanocrystal or the nanoparticle size with that of the dendrimer is formed. The aliquots of cadmium nitrate and sodium sulfide may be added to the dendrimer solution simultaneously or sequentially in either order. In the experiments, either 5 or 10 aliquots of each reagent were used so as to produce the desired nanocomposite with concentrations as has been already told. In addition to the methanol formulation of the CDS or the dendrimer nanocomposite, a 10% methanol to 90% water formulation was also investigated. The nanocomposite preparation utilized 1:9 methanol to water solution ratio of the particular dendrimer, cadmium nitrate and sodium sulfide instead of the pure methanolic solution, but was otherwise conducted the same way. The rationale for the 1:9 methanol to water solvent system was simply the general desirability of water-based chemistry. The methanol served for the initial dissolution of reagents and was then added to the water. For the development of physical fingerprint or the treatment akin to the dye staining procedure, the fingerprints that is fresh to 1 day old were placed on aluminium foil and Ziploc sandwich bags. Some of the samples were fumed with cyanoacrylate ester before staining with the nanocomposite, while other fingerprints were stained with the pre-fuming technique. With nanocomposites in methanol, the best results were invariably obtained regardless of the concentrations when the nanocomposites involve the generation of 4 dendrimer rather than generation 0 or 1. This dendrimer is the focus of the chapter that follows here, or the theory that we are following after the nanocrystal composition for the detection of fingerprints. With this dendrimer concentration greater than 10 to -4 molars, solution was quite tacky and produced too much background via the indiscriminate adherence to the sample rather than the preferential adherence to the fingerprint on the sample. Thus, the Dendrimer concentration employed ranged from 2 to 8 into 10 to the power minus 5 molar in methanol, as well as in the ratio of 1:9 methanol is to water preparation. Fingerprint staining with the methanol and methanol is to water formulation simply involved dipping the aluminium foil and polyethylene samples and then letting them dry completely. In the customary staining with the fluorescent dyes such as the rhodamine 6G, the article is immersed for not more than a few seconds or is sprayed with the dye solution. In the CDS or the Dendrimer nanocomposite case, however, the immersion involved not seconds but hours. Methanol solution dipping was not successful with the unfumed fingerprints because the aggressive methanol tends to dissolve away the fingerprint. Cyanoacrylate ester pre-fumed fingerprints, on the other hand, developed readily on both the aluminium foil and to that of the polyethylene. The long immersion times required for the fingerprint processing suggests that a chemical reaction of the amino acid functionality of the dendrimer with that of the carboxylic acid or ester of the fingerprint, or for that matter perhaps with the cyanoacrylate ester functionality, is involved rather than the physical preferential deposition as in the staining with the dyes such as rhodamine 6G. Now we will be studying about the use of the cadmium selenide nanocrystals. The fabrication of cadmium selenide nanocrystal involves high temperature chemistry that must be performed under an inert argon atmosphere, which comes with considerable difficulty and hazard. At present, these nanocrystals are not commercially available except perhaps in research that is taken in milligrams sample quantity and is at a high price. However, companies are forming at this time and such that no one can anticipate that a range of the cadmium selenide nanocrystals will become commercially available in the near future. Cadmium selenide quantum dots or the nanocomposites are typically encapsulated with zinc sulfide. The encapsulant, quite apart from its productive function, serves as the substrate for the attachment of conjugating ligands that are designed to selectively label the substances of interest. The work done to date on thus the functionalized quantum dots has primarily targeted the biotechnology arena, and the functionalization has tended to involve the carboxylate and the amino groups. Because of the high cost and low availability of the cadmium selenium or the cadmium selenide nanocrystals, we have to date only the addressed fingerprint development with carboxylate functionalized ones, that is obtained from the Quantum Dot Corp Palo Alto, CA. Diimide mediation of the chemical fingerprint labeling was essential, that is fingerprints of 1 month old on the aluminium foil. Heating was not useful, thereby destroying the nanocrystals. Nanocrystals are generally stored at low temperature of about 4 degrees Celsius to prevent flocculation. Studies show that no fingerprint development was obtained at that temperature, even with the sample immersion for up to 5 days. At a room temperature, 24-hour fingerprint immersion in water solution containing 1 micromolar concentration of the water-soluble cadmium selenide or zinc sulfide carboxylate functionalized nanocrystals, and in 8 micromolar concentration the water-soluble 1,3-dimethyl aminopropyl 1,3-ethyl carbodiimide hydrochloride produced development of the luminescent fingerprints. The low nanocrystal concentration itself was dictated by the limited nanocrystal supply. In keeping with the semiconductor characteristics, that is the broad band structure characteristic in absorption, They utilized nanocrystals luminesced under excitation that could range from the ultraviolet to the red band. This makes for greater flexibility in terms of the excitation from the light source, and the comparatively rather sharp red luminescence peaked at a wavelength of 635 nanometers and had full width at half maximum of 35 nanometers, that is comparable to that of the molecular fluorescence. Luminescence lifetime measurements were best interpreted by two compartment fits, and these yielded components of about equal intensity fraction and lifetimes of 3 and 9.5 nanoseconds for the carboxylate functionalized nanocrystals and of 6 and 24 nanoseconds for amino functionalized ones. Note that the nanocrystal sizes can be tailored to produce the luminescence ranging from blue to red. Typically, luminescence lifetimes would increase as the emission of the blue shift. Next is the investigations ongoing in nanotechnology as an aid in the fingerprint detection. From the work on nanocrystals and nanocomposites done to date, including the utilization of dendrimers and the functionalization with the carboxylate and the amino groups, it would appear that a fair understanding of the involved chemistry is at hand, and that this is a chemistry that potentially offers much flexibility in the fingerprint processing. Thus, the current work is the beginning to tackle the formulation of the various recipes of practicality. In particular, the aim is to devise procedures for porous surfaces, especially the papers, which thus far remains elusive. Furthermore, work is also in progress to optimize the staining type approaches in order to concert with the cyanoacrylate ester fumed fingerprints. In addition to the utilization of the nanocrystals and the nanocomposite, we are expanding the exploration of the lanthanide complexes into the dendrimers. The driving force behind is the fact that the very long lanthanide luminescence lifetime permits time-resolved imaging by the time-gated techniques, which are simpler than the phased resolved counterparts. The diimide mediated amidation reaction that forms the core of the chemical fingerprint development technology involves an intermediate ortho-acyl urea derivative of the carbodiimide that is reported to be unstable. Instead of the nucleophilic attack by the primary nitrogen of the amino compound so as to form the amide, it may undergo the hydrolysis, regenerating the starting carboxylic acid and producing a urea derivative of the carbodiimide. To assess the amidation reaction, N-hydroxysuccinamide has been reported in the biochemical application also. The compound produces a stable active ester that then reacts with the amino compound so as to yield the amide. While the biochemistry literature may at times be a good guide to chemistries applicable to the fingerprint context, it is worthwhile to reiterate that there is a major difference between the two fields. In that chemistry, one generally wants reagent and analyte to be soluble in the same solvent, whereas in the fingerprint situation, one must have incompatibility of the fingerprint and the reagent. Otherwise, the fingerprint detail will bleed at the best or be obliterated altogether. Now students, let us summarize this module. The most problematic of fingerprints are the latent prints that are not readily visible and that require development of chemical or the physical means. Nanotechnology is being used to engineer the particles so as to overcome this particular problem. Semiconductor materials such as cadmium sulfide, cadmium selenide, and many more, which are normally not luminescent, can become intensely luminescent when particles typically in crystalline form can be very small, that is of the order of nanometer in size, and such particles can be quite robust also. These features are valuable from a biotechnology perspective and are in principle equally pertinent to the fingerprint context, thus prompting a study of their potential utility in the fingerprint detection. In photoluminescence detection of fingerprints, the staining approach generally tends to be more effective when applicable to the article under examination rather than the dusting procedure. Because staining with fluorescent dye after the cyanoacrylate ester fuming is a very successful fingerprint detection methodology, diacetyl sulfosuccinate capped with the CDS nanocrystals dissolved in heptane or hexane can also be employed. Any preferential adherence of the organically capped cadmium sulfide nanocrystals to unfumed fingerprints would involve non-polar fingerprint constituents such as lipids, and these are readily dissolved in hexane or heptane. From the work of nanocrystals and nanocomposites done to date, including the utilization of dendrimers and the functionalization with carboxylate and amino groups, it would appear that a fair understanding of the involved chemistry is at hand, and that this is a chemistry that potentially offers much flexibility in the processing of fingerprints.